Continuing our exploration of imaginary and complex numbers, we will now look at multiplication. So we've already done addition and subtraction as our basic operations. Multiplication is the next one logically that would fall in line, followed of course by division, but we're not quite there. So good news is that in a lot of ways, multiplying complex numbers is very much like multiplying polynomials. There's just that one extra step that we need to be looking for, like terms and potentially changing the way numbers look based on having an I squared, I to the fourth, or I to the third, anything like that. So we've got options here on how we want to do this. And we're going to demonstrate kind of two different ways. We want to rewrite it in the form a plus bi. We've got the quantity 2 plus I times the quantity 3 minus 4i. So I'm going to start this off with an area model because, again, if you need that area model to show the representation, I think it really helps to organize the information. But I'm also going to show you a way to do that later without. So setting up my area model, again, it really doesn't matter which column I put which binomial, but just as a matter of convention, the first one I'm going to put on the left side, and the second one I'm going to put along the top. So the next step is once I've got that area model set up, I'm going to go ahead and fill in the boxes with the appropriate pieces. So here I would have a 6, a 3i, a negative 8i, and this would become negative 4i squared. So just like when we did polynomials, the diagonals are going to identify for us like terms. So I can see here the 3i and the negative 8i are definitely going to be like terms. What's a little bit different with complex numbers is there's actually another pair of like terms in disguise along the other diagonal. We'll see that when we rewrite our terms. But when I take these pieces out, I'm going to have 6. This is going to become 3 minus 8, which is negative 5i. And then negative 4i squared will become really negative. Well, I'm just going to write that negative 4i squared, and we'll change it in a second. This will become a positive 4, because I squared will become negative 1 times a negative 4. So putting those together, the 4 here with the 6 here would give me a 10, and then minus 5i. Again, a complex number for my final result. The second one's very similar in structure, and the result's going to be a little bit different, but it's the same basic idea. We're going to take 5 minus 2i times the quantity 3 plus 2i. And so when we do that, filling our boxes out, we're going to have 15, negative 6i, positive 10i, and negative 4i squared. Again, along the diagonal right here, I've got my like terms. So starting this off, I'm going to have 15 plus 4i, and then minus 4i squared, which again, we know will turn into a positive 4 because of the I squared becoming negative 1. So positive 4 plus 15 is going to give me 19. I guess I should have boxed my answer over there. And then plus 4i. So that's how we can use the area model to multiply. But there's another way we can do that using something called double distribution. So essentially what we're doing is we're taking our first term, 2, and distributing it to both of those. So 2 times 4 would give me 8. And 2 times negative I is negative 2i. Then I'm going to continue distributing the 3i. So 3i times 4 is going to give me 12i. And 3i times negative I is negative 3i squared. Oh, put the like terms together. 8 and 12 is 20. Oh, I'm sorry. My goodness, I don't know why I'm putting those together. My mistake. I really should be looking at the 8 and the negative 3i squared. So the negative 3i squared will become a positive 3, plus the 8 gives me 11. That's much better. And then the negative 2i and the 12i should give me 10i. And same thing on number 8. Let's see if something magical happens on this one. So when I distribute the 2, I get 4 plus 6i. And distributing the negative 3i, I've got negative 6i minus 9i squared. Again, looking to combine like terms, I've got a 4. This negative 9i squared will become a positive 9. So my end result, I'm going to have 13. And the 6i and the negative 6i end up canceling out. So that's strange. we ended up with a real number answer by multiplying two complex numbers together. Well, if you looked at the polynomials, or I guess binomials, you might have noticed something about them. So the real number components were exactly the same, but the imaginary components were just opposite signs. So a negative 3i and a positive 3i. That's what's called a conjugate, where we have one quantity that's almost exactly the same, but the term in between, positive or the sign in between, positive or negative, is different, but everything else is identical. Well, what happens is when we multiply those things together, we end up getting a real number for our answer, which will be very useful when we look at division to try and simplify some things. So our last thing we're going to do here is we're going to find the conjugate of this complex number and then find the product of the complex number and its conjugate. So on 19, when I've got a complex number of negative 3 plus 2i, my conjugate of that is the same real number component, but the opposite imaginary number component, so negative 2i. So multiplying those, negative 3 plus 2i, negative 3 minus 2i, when we multiply the negative 3 through, we get positive 9 plus 6i and negative 6i minus 4i squared. Again, the middle terms are going to cancel, and so we end up with 9 minus 4i squared, which will end up being 13. It's not always going to be 13, by the way, but just so happened twice that it was. Same thing on number 20. I've got 5 minus 4i, so my conjugate there would be 5 plus 4i. So multiplying those together, 5 minus 4i times 5 plus 4i. You want to be smart about this because I've noticed twice already that when we had conjugates, the I term, that term in the middle, would eventually cancel out, which is exactly what I want to have happen. So I actually didn't need to multiply this part right here or this part right here. So I'm going to be smart about it and just multiply the pieces that I really need. 5 times 5 is 25. And then negative 4i times 4i squared is negative 16. Oops, negative 16 I squared. Again, that's going to become a positive 16 with the 25 that's already there. And I end up with 41.